All right, so this is CNET 127, and this is the next to last class. All right, so I'm going to talk about fault injection and fuzzing, and then Rust. And I'll talk about the last chapter on the last day. The last couple of quizzes are available, but they're extra credit because I understand that people don't want to try to learn new material right here at the end of the semester. Anyway, so let's talk about fault injection and fuzzing. And I put it in the slide here so I wouldn't forget. We got money to pay the coach, Elizabeth, for the cyber competition team. So in the fall, we'll be back in the competitions like we ought to be. I was very much pushing for this because all the students that participated in the cyber competition team, they all went on to very good jobs. Some of them are working at places like Google and Amazon and Cloudflare, all kinds of great places. So if you are a relatively advanced student, this is the thing you should do beyond all our classes, where you really get up there and compete with Stanford and all kinds of other great places, and you really learn a lot. And you don't need to win, as far as I'm concerned, to win. You'll get a good job even if you don't win. We've never won the final. We won a regional, though, which is pretty awesome. And, I think being in the team at all is enough to convince many employers that you are really on the cutting edge and you deserve to get hired. So we're going to happen. We got the money. So I can say the details will be up to Liz. She'll have some kind of orientation and tryouts where you can compete for the team. But if you want to get ready, just start doing hacking challenges. I listed a few here. There's a lot more. Just practice on them. And anyway, so keep an eye out for that. That will be very good. All right, and so let's talk about fault injection. Fault injection is long been used to verify hardware, for example. So if you have any kind of electronics, you might wonder what would happen if the electric power has a problem. And so you might have electromagnetic interference, you might get inadequate power in a brownout, things like that. And so you would test your stuff to see if this will break it or if it will make it stop working. And that's part of quality assurance, where you test the product you're making to see if it is strong enough to withstand normal use. And so you can automate these techniques, or you can use manual techniques to see if there are faults. And I want to show you little pieces of a fun video. I made a little chart. This video is about a half hour long, and I don't want to play the whole thing, but it's exactly the right topic. And so I made a list of what parts to play. So let's start with the first 1 minute here. All right.
What if you had a couple $1 million stored on a piece of silicon the size of a postage stamp, and it was protected by a password that you forgot? Chips like this are in all sorts of different types of hardware wallets out there that are supposed to be used to protect your recovery seeds and your private information in the world of cryptocurrency. But a lot of people forget their passwords, and if you forget your password, if you can't access the information on the chip, you're out of luck, you're out of money. That's the problem we're dealing with today. Some guys contacted me out of the blue. They have a Trezor hardware wallet, and they have a couple $1 million stored on a device like this, and they want me to see if I can hack the wallet, defeat the security, and get access to the information so they can prove that the money is theirs. I'm Joe Grand. I'm a hardware hacker, computer engineer. Hacking a product like this is an amazing challenge. It's like solving a puzzle, and we really only have one chance to do it right.
All right, that's the start. Now I want to skip ahead a bit. All right.
Right. I knew that the attack would need to take advantage of something called fault injection, where we're basically causing misbehavior on the silicon chip inside of the device in order to defeat security. And what ended up happening is I was sitting here watching the computer screen and saw that I was able to defeat the security. The private information, the recovery seed, and the pin that I was going after popped up on the screen. I kind of didn't think it was right because that's not what I was trying to do, and ended up mentioning it to my wife later on. She's like, well, so you did it. And I'm like, I guess.
Okay.
All right. Let's go on to 13. So he revealed the key of his test unit by accident, but he didn't know how he had done it. This is, of course, very common.
I slept on it, woke up, came downstairs, looked through the source code of the Trezor device, because I figured at some point in that process, that recovery seed and that pin had to be moved into that RAM area that I was able to access through my debug interface. This is exactly why I can perform my attack. This memcopy function right here, I checked future versions of firmware. This was 1.6.0. In 1.6.1, the next small revision, that function had been removed and the whole memory structure actually had been changed. It turns out that I found an area in the source code where on PowerUp, the secret information gets copied into RAM, and then when I do my glitch to defeat the security of the chip to give me access to RAM, the contents are there and I can get them out.
It felt really good to help with something that I know nothing about.
So yeah, let me give you a rundown of like the whole setup, just so you can kind of get a feel for the process and what we're seeing. In order for this attack to work, we have to use a bunch of different hardware. There's a security feature inside of the microcontroller, inside of the Trezor, that prevents us from reading the memory contents. So what we need to do is figure out a way to defeat that security so we can read the memory. The security mechanism only happens on PowerUp of the Trezor device, which means when we're doing our attack trying to defeat that check, we need a way to power cycle the Trezor over and over and over again. In order to power cycle the Trezor, I'm using a device called the Phi Whisperer. We're just using it to power the device on and off. This glitch only works if we glitch the chip on PowerUp. So it's something where we have to turn the device on, try to glitch it. If it doesn't work, turn the device off, turn it on. Once power to the Trezor is applied, we want to try to defeat the security check at exactly the right time to trick the chip into thinking that we have access to it, when in reality, we shouldn't. To do that, we use a tool called the Chip Whisperer, and we're using an attack called a fault injection, or a voltage glitch. That basically means that we're trying to force the chip into misbehaving in some way that's beneficial to us. We're basically taking advantage of the fact that electronic systems are defined to operate within specific parameters, and the vendor can only guarantee functionality within that area. My question is, what happens when we operate the device outside of that? And that's what we're doing with glitching. If we can glitch the chip at just the right time, we're going to defeat the security, and then we can continue with our attack.
I feel like I'm back in school.
Yeah, I mean, it's like school, except the tools are way more powerful now.
And the stakes are a little bit higher.
Yeah. The way that we know that we've properly defeated security is that the chip will enable what's called a debug mode. And a debug mode uses an external piece of hardware like this to let a legitimate engineer normally read memory and do general debugging of a microcontroller. In the case of the Trezor, if we defeat the security feature, it will enable debug mode and only let us access one particular area of memory, which is the RAM. The recovery seed and the pin, that private information that we need, is copied into RAM. We also need to modify the Trezor device to allow us to connect it up to the rest of our hardware. That's going to look something like this. All of the hardware pieces are tied together with this custom circuit board, and if everything works properly, then we win. When Miles, my 9-year-old, came in here and I started doing this, I'm like, it's kind of like when you're glitching a video game.
Yeah.
You know, and like you find...
All right. Let's skip ahead again.
There's an eyelash on the table. Now let's get our scope on. Set this guy up. And so when I start this, it's going to start our full glitch attack, and it's going to go step by step trying the different glitch offsets until it hits. Let's just run the loop. So this is the main loop. It's going to power cycle, check over and over again if the debug interface is open. As soon as it works, we get that device ID, then we know it's wide open for us. I'm going to start it. Ready?
I'm ready.
Here we go. So now we wait. This is it. It's the police stakeout.
Yeah.
We sit here and eat donuts, and then a couple hours later, something good happens.
All right. And so let's go to 27.
Nothing to do. There's literally nothing to do. This is torture.
Hack the planet.
Ah! Oh,
Yes.
like it knew.
Yes.
I'm like, this is torture. Back to planet.
Oh, that's
my
awesome.
god. OMG, like they say on the internet. Okay, so that was 3 hours and 19 minutes, which is right within that sweet spot. Oh my god. But now the question is that too far in the boot process? Did we miss an earlier glitch that's going to keep the contents in memory?
Well, we'll wait to find out.
I'm already shaking. All right, I'm too excited. This is the literal money shot.
Yeah.
Right? Like, this is the money shot. Okay, so we glitched it. Now I'm going to run the external program to extract the RAM. Okay, we've successfully copied the RAM out of the device. Now we can run strings and look at that file which has been sucked off of this device. So we're done with this hardware. If the contents are in the RAM, we have it on my computer right now. I'm so nervous right now, you don't even understand. I don't know if you can see, like, sweaty palms. Sweaty palms.
All right.
Okay, ready? 3, 2, 1.
Yeah, buddy.
Woo! All right. Now, so what he's doing, to the extent to which I understand it, and I don't know the details, is I think he's using the power supply, where you cause the power supply to have a sudden dip or increase in voltage. And you do this at a certain number of microseconds after power comes on. That's why he had to try many tries. You turn it on and wait 10 microseconds, and you turn it on and wait 50 microseconds, some stepping forward in time. So the idea is it's booting up, and during boot up, there is one point at which it temporarily copies the secure memory to the insecure memory. And you glitch it at that point. It will then enter debug mode, where his hardware can empty the contents of insecure memory. So that's what he was worried about. Even though he glitched it and hit the debug mode, it was not clear whether that would be before or after the operation that copied the secure memory into the insecure memory. But it worked, as you can see. But that's how it works. And Joe Grand is a very famous hardware hacker. He made the DEF CON badges for many years. Did lots of hacks like this. There's a link to the YouTube, and I'm sure you can find more links there for him. But anyway, that's the essence of what this lecture is about, and in a sort of fun way. So he got somebody his $2 million back. And yes, a lot of people love hardware hacking. It's a huge thing at DEF CON. It's a big deal. Yep, a Schmidt trigger. When I find out, yeah, Schmidt trigger. Yes, I've heard of this, but I haven't done any of this. You're right, Schmidt. And he's using these devices just built for this purpose. So you can buy these devices just for doing this kind of attack. Yeah, good. Anyway, so here's some topics about this stuff. So the idea is, now you can do this. Now he's doing it by modifying the power supply, I think. And what we're going to talk about now is where you use data. Without modifying the power supply, you put in unexpected bits. So you generate network traffic, then you capture the traffic, and then you choose a series of inputs to see the fault injection engine. These will just be modified inputs. Then you inject faults into the input and deliver it to the server, and then you have some kind of monitoring to see if the server crashes or does anything else unexpected. That's the game here. So you got to make input, and so here, for example, they use IDA. By the way, usually you will find bugs by using the more uncommon features of software, because the ordinary features that it uses all the time are thoroughly tested, and they detect flaws in that and fix it. It's the side little features that aren't used much that often have bugs and often are out of date. So here it used an IDA file type, and if you would try to use the IDA file type, you could then get strange responses, is the idea. And so you can manually generate inputs by just typing suspicious inputs in a text editor. And this would, of course, be best if you intelligently understand the product you're trying to attack. You can have intelligent guesses what might break it. You can use automated generation, which is, of course, easier, but it's more likely to waste time on automated attacks that are not appropriate for the software you're attacking. And you can do live capture. This is a common technique. Yes, he used strings at the end. All he did was dump the memory to other memory, and then he ran strings on it to find the strings. That's all he did, to find the readable strings. That's the simplest way to find data in a memory capture. And apparently he was able to find a string that showed the password. So you inject faults into live network traffic. This is the easiest way. You record the traffic and then replay it by just flipping some of the bits. Of course, you'd have to modify the packets because packets have checksums in them. And then this all started from fuzzing. Fuzzing generation came from old dial-up modems that you run during a thunderstorm, and the lightning strikes would cause surges in the line and cause some of the bits in the modem to be misinterpreted, and then people would notice that their Unix servers would crash because of that unexpected input, and that was the beginning of this fuzzing, which just automates that accidental process. And so you can do open source. Now, you can do black box fault injection where you have software running and you're just sending in malformed input, but it's much more efficient if you recompile it with special code added in to improve and that's what the American Fuzzy Lop works. American Fuzzy Lop is a fuzzing product that is very difficult to use. That's why I never added a project to the course using it, but it is very powerful if you learn how to use it. But you do have to recompile your code with hooks so it can measure, go down to here and measure and see. You just take, see the question, how do you inject faults in data? The simplest way is just record data and then modify it and replay it. And at Cisco, we used to count dropped packets. Yes, absolutely. Yeah, dropped packets and pulses and such. Yes, but it's something to measure if your hardware or software is not working. Now, if you have closed source apps where you don't have the source code, then you can't do this, and all you can do is modify the input data. So you can have a modification engine. This is typically done for finding buffer overflows. So you inject variable size data, you try non-alphabetic characters, and of course you try, if you just randomly change characters, then you'll be changing things like spaces, which will blur two things together. See, if you change the space between the get and the slash, you'd change the method to an invalid method, and probably it would just be ignored. So it's more common to do something more intelligent than that, where you would just change the elements without altering the number of elements or the separation between them. So here you might, if you want to inject this fault, EI 2003, I'm going to inject these extra characters in a GET request. You put it at the beginning, you put it inside the method, you put it inside the file name, you put it inside the HTTP, and so on. This is what you do to inject a fault. You would start with valid data and then perturb it in some way and have a whole series of modified inputs that have been modified in some way and see if any of them cause an unexpected result. So another thing you can do, if you have input sanitization, which blocks unexpected characters, then you might not change characters, but just repeat them. So add more T's, add more slashes, add more H's or T's here, so that you're going to get past things that block forbidden characters, but you'll be increasing the length of things, hoping to perform a buffer overflow. And so you create a network connection, you send your modified data, wait and close it. Now there's a problem here. The Nagel algorithm is an algorithm to improve the efficiency of network traffic, and if you're sending a bunch of small packets, it will actually hold them back and group them together into one large packet, which normally is good and it makes the transmission better, but you have to disable that if you want to really try packets of all different sizes, which is what we're doing here. You want it to literally send the exact packets you're sending and not make any attempt to clean them up. All right, and then you have to monitor the faults at the other end. So the simplest thing is a debugger, where it'll just stop if there's an exception, and then you can find the exceptions. Now, the most important exceptions to find are access violations, because what you're hoping to find typically is overflows, and if an access violation typically means either that you have made it all the way to the end of something like the stack or the data section, which is not interesting because that's not exploitable, but more like what you're hoping is you have managed to inject data and some of your data ended up in the EIP, and the EIP has become a random stupid value now. and that would indicate you've got an easily exploitable vulnerability. So the most common exploitable vulnerabilities are access violation exceptions, although not all of them are exploitable. But other things like divide by zero and stuff are typically not exploitable if you find them. All right, and that's called fuzzing. So you can do it static analysis to analyze code that's not running. But the problem is, if you do find static errors in static code, you'll find a pattern of source glides that are considered not best. For example, you might find a SQL statement that does not properly parameterize the query. But it might turn out that all the data used in that SQL statement is always fixed, and the user doesn't control it, so there's no way for anyone to inject dangerous characters into it. So even though in principle that one line is not perfect, in practice it's not an exploitable vulnerability. So this is the problem with static analysis. You might waste a lot of your time fixing bugs that in fact don't really matter. Fuzzing is more scalable. Instead of looking through the source code, you send modified input to the thing and see if it crashes, and if it crashes, then you know it did respond to input, and that's more serious. That's more likely to be exploitable. That means I can cause a crash with malformed input. The very simple strings might work like just long strings, ... many times and so on, just to see if any buffer can be filled up and overflow. So one problem with fuzzers is the same. This is the virtue of the fault of the virtue I just described. You're not going to hit all the code with a fuzzer. You're only going to hit the code that you can reach from various kinds of input. So you're not testing all the code, but you are testing the most important part of the code typically. Another problem, though, is there might be special inputs required to reach part of the program, which is what I found when I was doing a lot of Android apps. There was an automatic tool run by CERT to find vulnerabilities in Android, and I went and found a bunch more vulnerabilities they hadn't found because I was filling in the forms manually. And their automated tester didn't know how to fill out a form to get to the next page. It would put random junk in the form, and in a lot of cases that would not be accepted, and so it would never get to the next page to test it. So anyway, so fuzzing is not everything. You supplement it with static analysis and other forms of testing, but it is an important part of testing. Microsoft tried not using fuzzing up until they developed Vista, and then Laurent Gaffey, hacker from I think Belgium, twice found blue screens of death vulnerabilities in Vista, the pre-betas, in like 10 seconds of fuzzing. And he humiliated Microsoft to where Microsoft added fuzz testing. Microsoft resisted this because fuzz testing is a random process. You never know when you're done. You send random stuff. You never know how long. It's not controlled. You just choose, well, we'll send 24 hours of random stuff. And if it doesn't crash, we'll say it passed that test. But it's not like very scientific or precise or anything. But now everyone, I think, accepts that you have to fuzz test your stuff because it's so easy to do, and you do find vulnerabilities. So there's a simple fuzzer called Spike, a simple engine which you can run on Linux. And I used to have a project in this class, but it didn't seem valuable enough to keep it in as a project. But this is just a very simple fuzzer. And so you can put in a string. This will put a literal string in. This will add a series of varying strings, a string variable. And it has a canned list of strings to try. So you don't have to make your own list. You can just use a standard list. You can read a message from the server. And so you can send a string and then read a message and see if it is the expected response, like everything okay or some other response. And so this would be enough to fuzz the Windows vulnerable server. You just send variable commands, trun space and then a variable command, and then this will hit the buffer overflow we used in the projects looking at the Windows buffer overflow. Can you do accelerated tests? Well, no, that's the problem. You run it as fast as you can, and typically you have to decide how long you want to run it. Laurent Gaffey found things after only 10 seconds, so that's exactly the kind of thing that bothered Microsoft. You don't know how long to wait. You don't know. I don't know. I guess you could have multiple machines and run faster. Yeah. So I mean, I don't think there is any clear measure of how long you should go. So here's what you'd see running this Spike script. Here's a bigger Spike script with more complicated inputs it's creating. And if you fuzz against the vulnerable server, it will crash right away because the vulnerable server, all you need is a long enough input, and around number 8 or 9 of the standard inputs is like a 5,000 character capital A, and that will make it crash. So it's easy enough to catch a very simple buffer overflow with this, but it's not that useful for more complicated things. And there's a lot of other programs out there, like Cluster Fuzz is one of many that Google put out that uses a whole cluster of machines, and you can put it online, and there's all sorts of fuzzing frameworks and ones out there that do this. It's never very easy. I never found a way to make it into a project that fits easily into this class. But it is a big part of quality assurance. So let's take a look at some Cahoots. Oh yeah, Cluster Fuzz, yeah. Well, that might be it. All right, so which process must be disabled? The Nagel algorithm, which optimizes network traffic instead of just leaving it exactly the way you wanted it. Yeah, and I see more questions. Your fuzzing product will change the variable string, just sort of like a dictionary attack, to a list of strings you have somewhere, and that program comes with a pre-built-in list. And that's the purpose. The purpose is to inject faults. So you take correctly formatted, valid inputs, and you modify them by replacing a string with a different string. So you're just creating nonsense input to see if it causes unexpected results. All right, so what's the exception that's most likely exploitable? An access violation, which would suggest that the EIP achieves some strange value, which might be from a value you input. All right, and what technique makes it easiest to see whether flaws are reachable? That's the point of fuzzing. It will only find defects you can reach from invalid input, and therefore they are directly connected to something under the control of an attacker, so they're much more likely to be exploitable. And which one of these operations waits for the server to send a prompt? Yep, that's read line. Reads a line from the server. All right. All right. All right.